Hello. Last time we defined the L hierarchy, rather like the V hierarchy, through indices alphas for all ordinals. So we defined a level of the L hierarchy was an L alpha. And recall L alpha plus 1, where this was gotten by looking at the definable power set over L alpha, as opposed to the V hierarchy, where V alpha plus 1 is defined using the full power set over V alpha. On the other hand, we then proved a lemma that showed that actually many of the properties of the V hierarchy also are valid in the L hierarchy, namely things about which levels contain which ordinals and the ranks of various levels. We saw that the finite levels of the L hierarchy, the Ln's, were the same as the Vn's. So this would mean that L omega is the same as V omega, the hereditary finite sets. But thereafter, we don't have much guarantee that every set is going to be constructible. It's possible that the universe L that we defined is a so-called inner model of the universe V of all sets. So an inner model we think of as being inner to V. It might be all of V. It's not necessarily a proper inner model. But an inner model should be something that's like the L we've described, right? It's transitive and contains all of the ordinals. So it's a proper class. And what we're going to be spending today doing is showing that all of the axioms of ZF hold in L. So L is an inner model of ZF. And in fact, we use the phrase inner model to mean three things: that it's transitive, it contains the ordinals, and it's a model of ZF. So that's our first definition for today. And then we'll go through the axioms of ZF, and we have to show each one in turn and work at it a bit to show that they're all true inside the L hierarchy. So we'll start here at 4.6, definition 4.6. So we define something here in general, not just for ZF. Let T be a set of axioms in our language L here. And let W be a class term. Then we say W is an inner model of T if those three things hold. W is transitive. All the axioms of T hold when relativized to W. And 3, the ordinals are contained in W. So if I were to draw it, it would look like one cone sitting inside another, just as I drew L inside V here. By this is a shorthand. Right? This means for any sigma in T, sigma holds in W. I mean, T may be an infinite set of axioms there. Right? So we write W is an inner model of T here. In fact, I shan't be writing this much in the course. And when T is ZF, we just drop the T. So our task today in the next theorem of Gödel is to show that L is an inner model. So this is 1939. L is an inner model of ZF. In this terminology, IML, right? In particular, what we're showing is that ZF holds in L. Now we say this, being in a model is said without prejudice as to whether it's all of V or not. All I've said here is, I mean, V satisfies these clauses for ZF. V is transitive, ZF holds in V, and it contains all the ordinals. So possibly W is all of V, right? And here, this says nothing about the relationship between V and L, right? A priori, right? L might be all of V, or L might be a proper subclass of V. But it is a proper class, right? Because it contains all of the ordinals. So what we have to show, we've already seen that L is transitive and contains all the ordinals. And that L is transitive. It's a question of the axioms. So we go through each axiom in turn. By going through each axiom group in turn. So, axiom of extensionality. Well, this holds because L is transitive. That's true in any transitive class. The empty set axiom. This is kind of trivial because the empty set is the same as the empty set as defined in L, and this is in L. Right? It's 0. So pairing here. Suppose I've got X and Y in L. What we want here is the pair set to be in L. So how are we going to justify that? Well, things get in L because they're defined in some way or other. So we need some kind of definition that's going to give us this pair set. And here are the components, X and Y. So if I think on one side at the moment, here's L. I've got an X and a Y. They're somewhere in L. And I want this pair set to be there as well. Well, these appear at certain levels. I can't make the pair set until I've got both X and Y. So I find a level of L in which both X and Y sit. Okay, so I just look at the larger of the two L ranks of X and Y. The L rank of X and the L rank of Y. Okay. So in the way I've drawn it, Y appears slightly later than X. This is the beta I'm talking about. down here. Right, so x and y are in L beta. That's all in short, this is a fancy way of just saying find an alpha or find a beta so that x and y are in L beta. And now I'll write a definition down that'll put the pair set in L beta plus 1. X and y, well, it's a collection of z's in L beta such that the structure L beta epsilon, this is going to think, right, I'm going to allow z's to vary over my v0. v0 is v1 or v0 equals v2 here. And my assignments, I'm going to let x be assigned to v1 and y to v2. And a z will get assigned to v0. So it's crowding up against the picture. There. So again, this notation implicit in here is this will go to variable v0, this will go to variable v1, this will go to variable v2. When I assign these gadgets to this formula here. So z can vary here. v1 and v2 here are fixed. I look at the different z's in L beta that make this come out true. Well, for this to be true, z is going to have to be either x or y, and nothing else. So this is this, by design. Right? So this then is in def L beta, which is L beta plus 1. So we've done it. We found a reason why if x and y are in L, then the pair set is in L, the unordered pair set. So we're in business there. Okay. And similar kinds of arguments are needed for the other axioms, which are of lesser or greater difficulty. Right? Union axiom. So suppose x is in L alpha. I want the union of x to be in L. That's what we're trying to show here. Well, I'll write down a definition for union of x. It's going to be the collection of z's in L alpha such that L alpha epsilon thinks. And now what is it to be in the union? It means there is something in x such that z is in that something. So I'll say there is a v1 here such that v0 is a member of v1 and v1 is a member of v2. And I'm going to have z's varying over the v0 variable here, right? v1 isn't a free variable here. So I'm going to have z substituted for variable v0, and I'm going to substitute in x for v2. I don't have to worry about assignments to v1 because v1 is not a free variable of this formula. It's bound by this quantifier. I mean, I could write something down here, but it wouldn't make any difference. But then, of course, what have I got? The z's that make this come out true are precisely those for which there is something in X for which Z is a member, here. So this equals this, and here. And now again, this is definable over L alpha, which is L alpha plus 1. Right, so if X appears at a level, the union of X appears at the very next level. If we want to kind of calculate things like that, where exactly? And the same for the pairs. If I look for the least level, beta, where X and Y have appeared, the pair is in the next level. Okay, so we're going to continue in this fashion. So X in the foundation. Right, so these last axioms require a little bit more, slightly more sophisticated arguments, right, I'd say. So let B be a term. So if B is not the empty set, right, then there is something, there is some X in B, so that X intersect B is not empty. Right? This is a statement of the axiom of foundation, right, for this term B. Right? So we want this to hold in L. Well, this is going to hold in L if and only if, and I'll just tease out what the relativizations mean. If and only if B, well, B interpreted in L is not empty. And then there has to be an X in B as interpreted in L here, such that X intersect B interpreted in L is not empty. Okay, so this is what it would, this is an equivalent way of stating the axiom of foundation is true in L for this term B. But actually, when you now look at this, if you step outside of L, and this is just an instance of the axiom of foundation in V using V superscript L. So this is an instance of the axiom of foundation in V about the term B relativized to L. So this is true in V. The axiom of foundation is true in V. So this holds. But that implies then that this holds. And that's all you have to do. Excuse me. I mean, this might look a little sort of smoke and mirrors or something, but all we've done is take what we want, the axiom of foundation, to be true in L about this B, and seen that we can express this, right, as something about the axiom of, the true axiom of foundation in V. So what about the axiom of separation? So let A be a class term. And we'll look at how A is defined. Maybe A is a collection of Zs such that this particular formula here, where I plugged in Z for V0, and maybe there's a string of some other parameters. Have been plugged in for the other free variables, if assuming the free variables of the formula are contained within these displayed ones here. So this is what Z looks like. So now suppose I take X and some string of parameters, Y vector there, and these are all in L. Right? So there's a finite list here of these Ys. So we're going to apply the reflection theorem argument, right? And it's precisely because we expressed it in the form that we did, it's because I wanted to use it at this very spot here. If you look at lemma 240, it expresses the reflection theorem there in terms of a hierarchy Z. So let's just look at this again. Right? Here we had Z as a class term, and we had a function that told us what the levels of Z were. And they were accumulated, the unions at limits. Z was the union of the Z alphas. And then for any formula, we could prove in ZF that this formula was absolute between a Z beta and a Z. So now we're going to use this with L's in places of Z's. Right? That's why we did it like this. I'm going to have L here. I've got a function that gives me the L alphas. Right? There's this definite function. The L alphas accumulate in this way. Right? We proved the L alphas increase. They're defined to be the unions of limits. L is the union of the L alphas. So I can conclude this reflection theorem, this reflection property here for L betas and Ls. Right? There are arbitrarily large L betas, which reflect the truth of the matter about a formula phi or a string of formulae phi about its parameters that are in L beta. Right? So we'll use that now. Right? So we're going to use lemma 240. L as Z and L beta as Z beta, etc. So if these are elements of L, then they're in some L gamma or other. We use lemma 240 to find a beta that's bigger than gamma with a reflection property. Find a beta bigger than gamma. so that we can prove in ZF, right, for all Z in L beta, phi the whole of Z and Y vector, the list of those parameters there. This will hold in L, right, if and only if it holds in L beta. I kind of got too many brackets around here. I don't think I need this. So I've got that the formula phi that's defining things in my class term, right, is absolute between this L beta, where the gadgets appear as parameters, and L. And now, see, the definability was defined using our notion of something being true in a structure. What we've got here is something being true via relativization in a term. So this is where the correctness theorem that I mentioned that we would need to use kicks in here. So by the correctness theorem, 321, 5z of y vector here holds in L beta if and only if L beta epsilon, right, is a model of here where I put in the z's and the y's. Here. So that said, that our notions of we define satisfaction and truth in a structure in this way, this was correct in terms of the interpretations that we'd done before. So I've done this because I want to write this here. Right? So putting this together, what do we have? If I look at the z's, okay, so we want, right, for any x in L, and these, well, we've chosen an x in L. We want x intersect A, right, as interpreted in L to be in L. That's what we're aiming for the separation to hold. So let's look at the z's in X, such that phi z here, I look at this set here. So this is the term A in L intersect X. This is the set of Z in X, such that phi Z Y vector here holds in L beta. using the reflection property that we've got here. And using this correctness idea here, this is the collection of Zs in L beta such, sorry, this is just a such that. It's just a vertical line. That's the satisfaction symbol here. Well, the formula I want now is the formula phi from here. And V0 is in Vn plus 1. Recall phi only had these free variables in. Y1 up to Yn. So this is a new free variable, Vn plus 1. I'm going to have my Zs vary over the structure, L beta. So Zs will be interpreted for V0 here. The Y1 up to Yn will be interpreted as will be interpretations for V1 up to Vn. And then there's going to be an X in here. Let me just emphasize that gets substituted in for n plus 1. Like this. And that's how we specify it. We're looking at those Zs that are in X such that phi Z Y vector holds. So we've picked all of this out. X being in L gamma means it's in L beta. L beta is transitive, so X is a subset of L beta. So all of the Zs that we're concerned about, those that are in X, they're all there in L beta. So this truly picks out AL intersect X. Right? It truly picks out these things here. And now we've written this out in a way so that this is definable over L beta, right? So that it's in L. So we have here AL intersect X is in L. So a slightly more lengthy argument there. Okay, next one is axiom of replacement. Right, so there's some fairly lengthy arguments for each of these. So it's quite it's quite a lot of work going into proving this theorem. What do we have here? Well, suppose that f is a term. When interpreted in L, it's a function. And we're going to look at its range on a set X in L. For the axiom to be true, we want the range of the function on X to be in L. That's what we're after. Okay, let's look, let as above. We defined rho sub L as the constructible rank function. So that was, if X was in L, the L rank of X is the least alpha, such that X was an element of L alpha plus 1. Okay. So what we're going to do is apply the axiom of replacement in V. So it's slightly odd, right? To prove the axiom of replacement in L, we apply it in V. And what do we apply it to? We apply it to the L function, right? After we've applied it to F, to things in X. So just think about what this is doing for a moment. X is in L. F is a function. So actually, I can think of f of L as being a function in V. So the range of this function in V on this set X is a set X. Sorry, the range of the function in V on X is a set in V. And we're doing something slightly more here. What we're doing is we're looking at not just where F, not just at the collection of things that are in the range of F applied to X. We're looking at what the L ranks of those things are. We're looking to see where in L the things in here appear. We need to collect them together to be a set in here. That's what we're trying to show. Note F on L on X is contained in L. Yeah. That's not a problem, right? L thinks this is a function and this is an element. So this is a set of ordered pairs. First thing in X, second thing, well, some other constructible set. So the range of F on X is a subset of L. So this is unproblematic. So, and then if I then apply the rank function, I just look and see what are the various alphas where the elements in this range appear. So row L composed with FL on X is contained in the ordinals. So this, by the axiom of replacement, right, is a set of ordinals. So again, axiom of replacement in V, this here is a set. Has a supremum alpha, say, in the ordinals. Now we're going to apply the reflection theorem again. Right? So find a beta bigger than alpha. So that by the reflection theorem, okay, in ZF we can prove for all yz in L beta here, f of z equals y, this holds in L if and only if f of z equals y holds in L beta. You see, all we were told about f was that it was a term and that it defined a function in L. That's all the data that we were given down there. F may have a very complicated definition. If I define it inside some L alpha, I might get a different answer if I defined it inside some L beta. But the reflection theorem assures me that there will be an L beta where the function gets correctly computed. And that's what I've written down here. So I'll pick a beta here that's bigger than alpha, where all the elements of the range of f on x occur in L alpha. So as f of L on x is contained in L alpha, which is contained in this L beta here, I can write f of L here on the range of x. This is the collection of y's in L beta such that L beta epsilon is a model of this statement here. There is a V1 in V2 such that f of V1 equals V0, and I'm going to assign y's to V0 here, and V1 is not a free variable, it's bound by the existential quantifier here, but I'm going to assign x to V2. So indeed, this just says L beta thinks there's something in x that gets sent by f to y. So y is in the range of f on x. And L beta is one of these nice places where the definition of f makes sense here. So now I've massaged this into a form where I can see that this is not just a subset of L alpha, it's definable over this L beta. So this then is definable over L beta, and so it's in L. So this instance of the axiom of replacement, after all this work, shows us it's true. Applied to x, this thing is in L. So that finishes the axiom of replacement here. Let's say axiom of infinity. Okay, this is no problem. Omega is in L omega plus 1. Right? So there's an infinite set in L. Indeed, there is this set which contains the empty set and is closed under the successor function. So that's okay. So that one's easy. And now comes another difficult one. In fact, the last one here. Power set axiom. So first here in the notes is displayed some equivalents. There's a list of equivalents. For every x, there is a y. So it's the y is the power set of x. Right? So that's a statement of the power set axiom. We want that to hold in L. So let's just tease it out, what this says here. So for every x, there is a y, such that for all z, if z is a subset of x, if and only if z is in y. So again, y would be the power set of x. I've just written out what that means. So this holds here, if and only if. Now I relativize the formula. For all x in L, there is a y in L, such that for all z in L, here, the relativization of this to any class term, transitive class term, is just itself. Right? So I'll just write that here is this. But then if you think about it, what this is saying, given a constructible set, there's a constructible set Y that is precisely the constructible subsets of X. Saying for every constructible set X, there is a Y in L, such that Y is the power set of X intersect L. It's kind of the point of writing this out. We pick up the subsets of X that are in L here. The axiom of power holding in L doesn't mean that for every constructible set, the whole power set in V is in L. It just says there is something in L which looks like, locally, like the power set. Okay, so this does not imply that the power set of X is in L. Okay. Maybe there's some elements and subsets of, there's some subsets of X that are not there inside L. So we verify this. And that'll do for establishing the power set. So pick an X in L. Power set exists in V. So the power set of X in L, this is in V by the axiom of power in V and separation. This is a set, and I'm looking at those elements of sets in this class term. I'm separating those out. So this is a set by the axiom of separation. So P of X is a set. And again, the axiom of separation, again in V, says power set of set X here, intersect the term L is in V. So what have I got? Power set of X intersect L here. Oh, sorry, I was too soon. I'm skipping ahead. So again, I'll look at the constructible rank function applied to this set in V. Again, in V, right? Constructible rank function applied to this set here. This is a set in V. It's a set of ordinals. So again, we let alpha be its supremum. Okay, now we get what we want. A definition of a power set of X intersect L. So it's a collection of things that are in L alpha that come from something. So L alpha thinks V0 is a subset of V1, and I'm going to substitute in Z's varying over V0 here, and X there for V1. So the Z's that make this true are going to be those Z's that are subsets of, well, X. But all the constructible subsets of X are there in L alpha. So this definition truly picks up all of the subsets of X that are constructible. And so, of course, now this is in def over L alpha. So power set of X intersect L, this is in L. And by our equivalences there just at the beginning, we see, okay, that means the axiom of power is true in L. So we're done. So that was quite an exhausting list of arguments showing that all the axioms are true, but we soldiered through the whole set there. So we now know that all the axioms of ZF are true in L. So we'll tease out some of the consequences of this in the next few lectures.